Welcome, everyone. Good morning, good afternoon, good evening, from whichever part of the world you're joining us from. My name is Ravi Sivalingam. I'm one of the global organizers of the tinyML meetups and tinyML talks. Two new sponsors, DeepLight and Kixo, along with our other sponsors, Edge Impulse, Reality AI, Maxim Integrated, and SynSense. Additional sponsorships are available. Please contact Betty at tinyml.org for more info. Our upcoming talks next are on August 18th by Mark Stubbs from Shoreline IoT and Urmish Thakur from ARM-ML Research. It's the same time 2 weeks from now. And please contact talks@tinyml.org if you're interested in presenting at one of our upcoming sessions, either in the global tinyML talks or in any of the local meetup talks as well. Just a reminder, as we're starting the talk, please do ask your questions in the Q&A window. If you ask in the chat window, I may not be able to see it. I will interrupt the speaker periodically and during the end of the talks to ask the questions. All right, so our first talk today is Low Power Computer Vision Meets the Real World by Venkat Rangan. Venkat is the founder of tinyVision.ai, a product design and consulting company specializing in IoT devices incorporating CV. Before tinyVision, he was a director of engineering at Qualcomm Research and co-founded and led the R&D of the ultra-low power computer vision product that you saw in one of our previous talks. Venkat holds a BS in electrical engineering from IIT Roorkee in India and a master's from University of Cincinnati. Take it away, Venkat.
Morning, afternoon, evening, everybody. Thank you for attending. Venkat, thank you for the introduction, Ravi. So a little bit of background about tinyVision.ai. As Ravi mentioned, have experience developing products in the more on the R&D side of things and really architecting systems meant for low power. And what we do is some product development consulting, fast prototyping, all the way from concept through small volume. Have access to an SMT line partner, Mcraft, local to Carlsbad in San Diego, and so we can build hardware quickly. tinyVision is also a lattice design partner and specialize in building hardware with their ultra low power ICE40 FPGA series. Specific to this talk, I do use that in my one of the products that I analyze. So that's the background about tinyVision. So today's talk is really more about some of the war stories, I guess, or an analysis from a high level, stepping back based on my experience, hopefully to help other people. Right? So when I left Qualcomm, I started thinking about exactly what it takes to build an embedded CV device. So yes, there are chips out there. And one of the realizations was that this is a nascent market. Even among experts, and this audience included, very few people or very few teams have the necessary knowledge that spans the broad gamut required to build an embedded CV device and bring it to market, right? There's no real standard platform. Think about Raspberry Pi or Arduino. What do you do when you want to prototype something, right? That's not there. Customers tend to have this very distorted view of what is possible based on TV or all of the media, right? I mentioned already, you need this, just to build an IoT device is not easy. Add to that optics, add to that image sensors, huge amounts of data coming at you, algorithms. It adds many more dimensions to the problem. Because it's a new field, the large players really haven't come in yet. And so getting parts, getting access to the talent is difficult. And similarly, there are NDA barriers everywhere you go. Right? So if you want to get access to a particular type of inference engine, it's not something you just go to DigiKey or something and buy it. That's just not there yet. Very few companies actually have non-NDA data. So I went off and over the past year, decided to address some of these issues and built a small 2 by 3 centimeter open platform. It's a system on module, tightly integrated. You can go download the complete design on GitHub. Right? That solves some of the issues. It has clean interfaces. It's a connector. Electrically very simple. It looks like a standard sensor to you. And it's production ready. So you don't have to pick up like a Raspberry Pi, do all your work, and then say, oops, what do I do for production? Right? It's meant for production. And this will be crowdfunding on Crowd Supply. So pitch for you to go and check it out. Hopefully you'll be interested in it. So the reason I mentioned this is because while I did the design, I also went off and analyzed for power, right? What is required in order to build an embedded CV system? And there's all of these issues that, all of these different fields that you need to be an expert at. There's a blue line in the middle of somewhere to the right of the screen. I'm going to cover really things to the right of it. Otherwise it becomes this huge, broad talk that doesn't focus on anything. So I'm going to specifically talk about low power, communications and optics. These are things that I feel at a system level can be addressed better. Right? I will touch on the others as well. So let's look a little bit on the hardware and software aspects. On the firmware side, there are all kinds of frameworks which you can take advantage of. The sponsors of this talk, there's TensorFlow Micro, ARM has their own libraries. Every inference engine vendor has their own accelerated libraries, and it makes absolute sense to go and leverage them, right? So nothing new there. On the prototype system, I've already mentioned this. You're going to hit this issue once you start prototyping your system, is what do you use, right? And so do be prepared for it in terms of time and negotiation of the business side of it. It's not a trivial amount of work here. And production, I'm not going to even talk about it. That's there's just, that itself is a huge topic, right? Now, as far as the AI side of things, let's start digging a little bit deeper, right? It's really important to decide what gets done on the edge versus the cloud or somewhere in between. There's all this fog computing and things, right? The reason you do that is it costs money to transfer bits, it costs money to store bits, and it costs energy. So it's very important to really partition your work very carefully. Do you want to take pictures and send them to the cloud? Do you want to process it locally? That decision is going to be key in when you develop a product, right? The philosophy that I use is really increase the information content at every stage. Effectively, it's compression, but not just your standard data compression. It's really saying what is happening in the image. That is compression to me. In the case of algorithms, it's really taking advantage of the use case constraints instead of trying to fight them. For example, if you're indoors, you don't have to deal with the huge lighting variations. You can take advantage of that. If your camera is not moving, you have another area that you can take advantage of. You have a wider array of wider range of sensors that you can take advantage of, right? The other thing I would also suggest is that while neural networks are really hot, that is not necessarily the right solution. They tend to be extremely expensive in terms of memory, energy, as well as time, right? So what has worked well for me is really cascading algorithms. So have algorithms that work at extremely low power, low complexity, those run all the time. And as you as you switch to the next layer of algorithms, you increase the complexity so that you keep dropping the dropping more information as you go forward. OpenCV is great when you have access to Python and a big machine or the cloud, but it's not something that's going to work for you when you design these little devices. If you have a novel application, it makes sense to go to OpenCV, prototype it quickly, but then very quickly go and dissect what's happening inside the algorithm. Because the contributors to OpenCV never had an embedded product in mind. Data sets, again, this is a huge topic. I'm sure other people will do it better justice than I do. So let's drill down a little bit more into the optics and image sensor side. Right? It's extremely application specific. You're going to have to think about how far away are you going to detect objects. If you're detecting people, for example, are you detecting just the upper half of the person? What is the field of view? And do you want to be, what is the latency? So that determines your frame rate, for example. Do you have access to power, or is this a battery powered application? And is the image meant for consumption by a machine, or is it a human? For example, like the ring case, humans are actually looking at it, right? Whereas other situations where you're saying, hey, how many people are in the room? Humans are never going to look at that image. And then there are, it's a continuum. Sometimes you need to do both. And form factor is a huge one. The reason I mentioned that is because once you have a portable device, you are limited by the industrial design. So the first set of constraints will start to determine what kind of vision sensor you need to use. So if you have a lot of motion, you want to use a global shutter versus a rolling shutter, but rolling shutter tends to be a little less expensive and a wider variety of sensors are available. What band do you want to operate in? Is it, do you need color, for example? Do you need to be able to see at night? Do you want IR illumination or not? A lot of sensors now starting to integrate motion detection, and that is really great because it significantly reduces the amount of data to be processed. Probably one of the least appreciated aspects is the lens. I liken this to a music system. If you have an expensive amplifier and everything else, if your speakers are not good, you're not going to get good sound. The lens is the first interface from which everything starts degrading. So your lens has to be good, and it is something that you really should be focusing on right at the beginning. Do you want a standard lens, off the shelf thing, or a custom one, right? How is the lens mounted, for example? Where are you going to get it from? What is the field of view? All of that is going to determine it. Oftentimes the lead time on a lens is longer than everything else. Placement is something I briefly touched on, but to think about it this way, where is your device going to be placed? Is it going to be placed in the roof? Is it going to be placed on the side of a building? All of those determine what kind of data sets you're going to use. It also determines how you're going to, what is the level of accuracy you can expect. A sideways people detection, for example, is far less accurate than doing top-down. So if you're in the roof, if you have access to the roof here, you do not have to deal with the occlusion of people as they walk. Right? So these are all things that go into the product design that is important to think about at the beginning. I'm going to dig a little bit more into power as well. And so what determines power, right? If you think about it at the highest level, this is based on your customer experience. Do you want your customers to be replacing batteries? Do you have access to wall power? And the third option is, of course, rechargeable, right? Do you want to do energy harvesting? Who owns that, the field replacement? Who's going to be changing the batteries if you're requiring batteries? How often is it? And how much is it going to cost? And who bears that? Based on that, you're going to have to come up with a top-down and a bottom-up approach to this, which is really a power spreadsheet of every single device, every single leakage path that power is going to go. Once you get to the realm of microamps, everything starts leaking, right? And you also need a bottom-up approach where you're actually taking measurements of real devices, because when vendors advertise their in the data sheets the minimum, typical, and maximum power consumption, that may not match exactly what your use case is. So one of my favorite devices is called a Joule scope. It's amazing. Just the dynamic range required to make these measurements is huge, and you'll see that a little bit later. The other thing that I have done in the past in my Vision SOM as well is to embed power measurement chips in there, in the device. You can always take it out when it goes to production, but what it lets you do is to measure the power in the field under real world conditions and log it. Right? The reason I bring up energy harvesting here is because you have computer vision, and that requires light. So the use case itself implies that you have a free energy source sitting around. Of course, it's not really free because it costs money to do it, but what it allows you to do, as opposed to say monitoring vibrations or monitoring something with a very low energy content, is light has a relatively high energy density. So it is possible, if you're outdoors, for example, to be completely battery free.
Venkat, mind if I interrupt
Yes,
here
of
for a
course.
few questions? Yeah.
Sure.
No, this is really good. I actually, if you leave out the slide, I had a couple of comments to make on this as well. I mean, the field replacement cycle cost, I'm very glad that you brought that up, because that is absolutely something that most people don't talk about, but it becomes very critical. I mean, one example that I've heard is like in retail environments, if you're replacing a person who's going and monitoring the shelves with cameras, but then if you need a person to go and change the batteries every 3 months on the thousands of shelves, then you're basically just moving a cost from a person doing task A to task B, and are you really getting the benefit of that? And many people might not, the customer might not be willing to, feel that cost. And for the energy harvesting part, what about when cases when there is when people want to operate in low light, or if you are energy harvesting outdoors, what happens at night? I mean, what do you need to do to kind of save up the power in the morning to use it during nighttime or during bad weather?
Absolutely, you make a very good point. You do not want to be moving, you want to be saving overall, right? Whether it's in terms of people as well as in terms of energy and cost, right? Overall cost is what we are trying to optimize here. As far as what do you do at night, all of that goes into the power spreadsheet. Right? The way I've done this is really assumed that say 12 hours out of the day, you do not have access to power. And so usually, because we are worried about human type applications, there seems to be a correlation, and your use case might be different. If it's dark, usually you don't have to do too much. Only when it's bright are you looking for things, because it's computer vision in the visible spectrum. Your camera tends to be not very useful at night. So you might have to, if you really want to see at night, you're going to have to blast the place with infrared. That costs a lot of energy, which usually is not battery friendly. So it automatically will determine the need for tethered power. Or you end up with a spreadsheet that tells you, hey, you need a solar panel of some kind if you're outdoors. So it all comes down to analyzing your use case, and you have to make assumptions, right? How many days of bad weather are you in that particular region that you're deploying your device?
Yeah.
Do you
Whether
expect
you're
it?
in San Diego or in Seattle, I guess it makes a big difference.
Exactly, exactly. Yeah, you may end up with 2 or 3 different sizes of solar panels, for,
Mm-hmm.
depending on what your use case is. If you're in the middle of a forest, for example, I mean, you're not going to be changing batteries there. You are
Yep.
going to have to do energy harvesting of some kind.
Right. Right. One more question. Did you face any problems with versioning of libraries, like especially the ML libraries, and compatibility issues are associated with that when you're developing your code?
I did not have to um, deal too much with that, but yes, that is certainly a problem. For example, the TensorFlow libraries switching to 2.0, there is a lot of friction there. So yes, that can be an issue as the field is changing very quickly. So it is not easy to keep up with, because 6 months you don't touch something, you end up with a whole bunch of things you have to do before you get started again.
Yep.
Yes, it is certainly an issue. Yes.
Okay. Just a reminder for the audience, please use the Q&A tool to ask questions, and the slide PDFs and the recordings on YouTube will be available tomorrow. They'll be posted on the forums and youtube.com/tinyml. Thank you, Venkat. Please go ahead.
Okay, so let's dig into the communications aspect. Why do you need communications, right? The real fundamental reason is you want to communicate to and from the device. So you want to be able to send data back from the device, also to be able to configure it and tell it what to look for. You need a heartbeat to say that it's alive or is it dead, right? You need to be able to update it later in the field. As software and as models change, you need to be able to update it. Maybe your use case requires devices to communicate with each other, and we'll go over a possible reason why, right? So based on these, you end up with, again, the business model that drives you, which is it takes money to transport and store bits, right? You need to be able to think about whether the bits are transferred over your own network, which you have leased from, say, any of these 4G networks, or do you have a Wi-Fi that, or a BLE or some other way that you are expecting the customer to provide. Each has its own benefits and disadvantages, so this is something you have to go look at it. One thing I would tell you is that 4G networks deployment is not trivial, right? You can't just pick up a module, start sending bits and expect it to work. The reason is because you need to worry about deployment of SIM cards, for example. How are you managing the data? Who's using how much data? And signing agreements for volume, right? These are all things that we don't usually think about when we build a product or a prototype and say, okay, it works. It's not working until the business side is worked out. And the technical side of it is 4G networks have a huge number of parameters that need to be tweaked if you really want to get to the lowest power. We'll go over that as well. This determines what kind of topology you want to use, whether you want to have aggregator nodes, do you want devices to talk to each other so that you can have a mesh? Privacy, right? If data is going over a customer's network, who does the data belong to? And can somebody access it? You need to, usually latency is not an issue in some of the low power domains, but it could be, right? Energy is a big one, because if you're sending data over 4G versus BLE, it is certainly it's quite different. That will determine what kind of standards you want to use. And there's a wide array of them. Right? So let's look at a typical 4G link. This is from the datasheet of a Sierra Wireless Cat-M1 and NB-IoT module. What I did is went off through the datasheet and said, where is the power supposed to go? Right? There's 4 different states they advertise where you're sending a message. There's one waiting, the tau is where you're receiving message, waiting to receive a message, and then there's power saving mode and calibration. So if you go through the spreadsheet, you end up with, for one short message per hour, about 20 to 30 milliwatt hours per day, right? One thing I would like to recommend to people, please don't count energy in milliamps. Milliamps is not a unit of energy. It's really milliamps at the battery. People forget the milliamps at the battery part and say, my device consumes 2 milliamps of power. It's not, right? So please use the right units. You end up with most of the energy being spent in the power save mode, right? So this is the spreadsheet based approach. Now, if you look at, so this is the reason that I mentioned an aggregation node is quite a bit of energy is spent just waiting, doing nothing, right? So let's look at this in, so I put the module on a Joule scope, and this is what you see, right? From power up, there is a long registration time. If you see the x-axis is really in seconds, it takes about 1.5 minutes from power up for it to actually register on the network. And once you're registered is when you can start receiving and sending data. The other thing I would point out to you is the y-axis is in watts. And that's a tremendous amount of peak power. It's about 4.5 to 5 watts of peak power. It's for a short time, so don't expect a coin cell to be able to supply this, right? It's not feasible. So you really need to think about it. A lot of energy is consumed just in the registration process. So you can't, it may not be feasible to shut down the module completely, wake up, and then send a message, then shut back down, right? So 4G, while its deployment is very easy, you don't have to worry about the customer, where what their network is. You do need to think about power very carefully. And this can also drive the need for an aggregation node, which is powered. And everybody talks to it through a much lower power protocol, say BLE. So if I looked at the complete system now, I took my vision module and a 4G net, the 4G module, connected it to a small Cortex M4 class processor, and said, okay, what happens in my typical use case? So so there's 4 possibilities. We are in power save mode where you're not doing very much. You're just in the deepest power state you can be. Dormant is where you're waiting for something to happen, and you're depending on the image sensors motion detection. And then you're doing inference. In my case, it's about 10 milliwatts at 10 frames a second. And then the rest of it is communication, right? So by saving a milliwatt even on inference is not as much as useful as looking at the rest of the communication piece. So this is what I mean. You have to be a little careful when you look at, by looking at the entire system rather than just at your own little, is my camera more efficient than the other camera, right? So be careful of that. So some of the conditions under which this was modeled, I'm sure your use case is going to be different too. Okay, so I wanted to show you a demo here of an HM360 sensor. This is from Himax. It's a QVGA sensor, and it has in-sensor motion detection. So the green squares are will turn red whenever there's motion, and then we look at the power, right? I've recorded this so that we don't have demo issues. This is a monochrome sensor, and you can see that when I walk in, the pixels only where there's motion is detected, turn red. These are super pixels. There's about 16 by 16 grid. You can use that to really trigger the rest of the system. So if you look at it from the power point of view, this is on a Joule scope. You can see that this is at 1 frame per second, and it's the average power being consumed is of the order of 150 microwatts, right? And that's a pretty good power consumption, you'll see that whenever it detects motion, you'll see some of the power. For example, here, you can see the power went up a little bit and the average power consumption went up, right? So this is the sort of analysis that I'm suggesting that you do, is you take a real sensor, put it through a spreadsheet, and then actually put it on the bench, try it out. So that's all I had. And I'm open for questions.
Thank you, Venkat. Yeah, this was really good, and we have quite a bunch of questions. One of the things I would like to ask, if you go back a couple of slides, um, yeah, here in the pie chart with the communication. So, do you recommend then that we probably sense more frequently and communicate, less often? For example, sense for, I don't know, several minutes, collect all that information locally, and then transmit that information once every minute or once every hour.
If you see the pie chart that I showed before, right, which is where is the energy spent in this modem itself? Most of it is spent just waiting, right, in this deep power state, power down state. So I think the way to really address this is to say, hey, you know what? Most of my energy is going in communication. Where is it going? It is going into the deep power down state. So either I upsize my battery to be able to handle this, or I do a hybrid approach of a network where you have small nodes that have efficient communications as compared to this. And I mean, this is really the bottom line, right? You can't do much about it at this point. The communications is what it is. This is assuming a well-optimized system. By increasing the frequency of sending data, you may not really affect this too much because a lot of it is just spent sleeping. Once an hour, I tried making this once every half an hour, and it didn't have too much of an impact. But it really depends also how much data you're sending. So I think you have to go through the details really to come up with an answer for that.
Absolutely. A question about whether automation is a priority in these systems. For example, basically, is the system design keeping in mind that there is no human in the loop, or is it going to be like more human support systems, or what kind of automation, what level of automation are you looking for in the end product?
I'm sorry, I didn't understand that question.
No, so I mean, the idea is the system design keeping in mind that there's no human in the loop, right? Like, so nobody will be interrupting the process, if you kind of say it that way. Like, people are going to be collecting information over a longer period of time and perhaps looking at collected statistics versus working with it on a continuous basis.
So what is the question? I see that happening, but I don't understand what the question is trying to ask.
I think we need a little more elaboration from the question asker. So
I'm sorry.
Let me move. No, that's okay. That's fine. Let me move to another question that has been uploaded. Okay. Could you briefly touch upon the multiple tiers of CV algorithms that you mentioned?
Sure. Think about it this way, right? You have the possibility of an image sensor having motion detection. They tend to be rather crude if they're not as sophisticated, because that's really what you need, right? You need something basic that triggers. It may have a high false positive rate. Then once that triggers, you send the image over to the processor. That takes energy. So you want to minimize that. And that's the reason you have in-sensor motion detection. Once you get it into your sensor, you may have something like a background foreground detection model that does a better job of change detection, right? That is one layer, for example. Based on that, you can say, hey, you know what? change happened in this particular region. So all the little red boxes that you saw moving around, draw a box around that and say, this is the region that needs to be looked at. And I think the next talk is going to also talk quite a bit about those sorts of approaches where you have cascading algorithms of increasing complexity.
Mm-hmm. Absolutely. Another question is about whether the ML on chip requires neural architecture search and training based on system conditions, or is a pre-trained network usable off the shelf?
So is that specific to the module that I designed, or I'm assuming
in general as well for low power CV?
power is certainly should be an input to a neural architecture search, right?
Mm-hmm.
Power, or I should say energy. I shouldn't say power. Total energy consumption, not just per inference, but for a particular use case. Combine that with all of the usual things that people talk about, which is memory, bandwidth to the memory, as well as amount of memory, as well as compute and inference time. So yes, you do need total energy as an input to a neural architecture search that would, I assume, skew some of the results that we typically see in literature a little differently.
Absolutely. So I guess the conclusion is we can't just try to take something off the shelf and try to fit it in any embedded device. We have to develop it with an eye on the actual embedded device's capabilities and power consumption.
Yeah, I couldn't agree more. In fact, I would go out on a limb and say if you're going to pull something off the shelf, expect it not to work.
Yep.
It is going to work, but it's barely going to work, and then you're going to be stuck, right?
Yeah.
It's better to anticipate that as an issue and then figure it out from almost first principles.
Right. There's a question about low power sleep and how much, and there are different kind of versions of sleep from my understanding, and how does that help with the power ratios that you talked about? Like going to complete low power sleep when you're not, or even sensing infrequently or communicating infrequently. I guess it kind of goes back to the question I talked about transmitting infrequently. But
yes,
yeah.
so going to low power modes is important, right? And you want to do it frequently. You do want to be in the lowest power state possible for as long as you can. The question then comes, how do you get out of that? What makes you get out of that mode?
Mm-hmm.
You may, one way is the in-sensor motion detection. People use PIR sensors or other kinds of sensors, which or say an ambient light sensor, right? When light changes, you wake up and say, did something happen? Or if a PIR, which for people who don't know, is a passive infrared sensor. It's a sensor that's sitting around in, say, these lights that turn on and off automatically. They consume extremely low amounts of power, and they sense in a different modality. So that can work in darkness, right? So you do want to go to sleep, but make sure you know how you wake up from sleep. That's important. Otherwise, you're going to miss events. You're also going to have trouble when you wake up. How do you know your higher level algorithm is in a good state? For example, change detection. If you're having background foreground detection, if the scene has changed from the time you fell asleep,
Mm-hmm.
you're going to have trouble there, right? So some of these, it's good to just walk through and anticipate some of these issues. So,
Well, thank you. There are a few people asking about your module in your crowd supply page, which I think the link is available on your slides. So we'll also share that in the forum. In the interest of time, I know we're a little bit over time. We will proceed to the next speaker. Thank you very much, Venkat.
thank you very much.
So I'd like to thank our sponsors. DeepLight. DeepLight uses AI to make other AI faster, smaller, and more power efficient. Edge Impulse. Edge Impulse enables developers to create the next generation of intelligent device solutions with embedded machine learning. Maxim Integrated, sorry about that. Maxim Integrated enables edge intelligence with sensors and signal conditioning, low power microcontrollers, and advanced AI acceleration. Kixo automated machine learning platform that builds tinyML solutions for the edge using sensor data. Reality AI. Reality AI is the leading product development environment for edge AI and tinyML on microcontrollers. And finally, SynSense. SynSense builds ultra-low power sensing and inference hardware for embedded mobile and edge devices. Just a reminder for our next tinyML talks on August 18th, same time. Please contact talks@tinyml.org if you are interested in giving a talk. And as I said, the talk material, the video and the slides will be posted on the forums and the tinyML YouTube channel. Please check it out there. Thank you, everyone.